yesterday, again, you were asking a lot of questions. Please keep asking a lot of questions. Let's see if you can ask more questions than the other day, so we can keep the class as interactive as possible. And yeah, we'll see. We don't need to go until that late. We can, yeah, that's fine. But let me begin with, as always, just refreshing your minds from what we saw yesterday. So yesterday we were focused on the question of how gravitational waves are being generated. And for that, we were studying the emission of gravitational waves in flat spacetime generated by some first generic energy momentum tensor. And then what we saw is that when the observer is far away and we are in the the source is moving at low velocity, then actually we can solve analytically this emission of gravitational waves, and this is actually sourced by accelerated quadrupole moment. So that's a very important result that tells us how gravitational waves were generated. This Mij is the quadrupole tensor, Mij, which just comes from the integral of the 0,0 component of the energy momentum tensor. And because it's the quadrupole, you have twice the positions. So this was general for any given energy momentum tensor. And then we focus on the case of two compact objects, actually 2-point masses for the purpose of our study that were far away, orbiting in a circular orbit. And then what we found is the expressions for the amplitude of both the plus and the cross polarization. In order to get this result, we had to introduce one parameter, which is the chirp mass, which is a mass parameter that has a combination of the M1 and M2. So here, this is for H plus, and then for H cross, it's essentially the same, except for the dependence with inclination, which is different, and also the phasing of the wave, which is the phase. And there was this important parameter that I just alluded, which is the chirp mass, which is M1 times M2 to the 3/5 divided by M1 plus M2 to the 1/5. And then the other element here is the phase of the gravitational wave that comes from the chirp of the signal. So we derive that the frequency evolution of the gravitational wave is also just determined by the chirp mass alone. So Gm chirp, c to the cube, 5/3, f to the 11/3. And with this frequency evolution, actually one can compute the phase of the gravitational wave just by integrating the orbital frequency, which is 2 times the gravitational wave frequency. No, sorry, the gravitational wave frequency is 2 times the orbital frequency. And then the gravitational wave frequency, we can get it from this expression. So at the end, what you get for the phase, and this is something which I think I didn't put yesterday, is that you have this relation for the phase, which evolves with some power of the shear mass and also the time to coalescence. So with some initial phase. So this T is the time that one has left to merger, and you can put also numbers for this. So you can compute this is something that I said in words, but I think it's good to have the formula as well. The time to merge for a given gravitational wave is given by 5 to 56 1 by f to the 8/3, and then g m chirp c cube to the minus 5/3. And then if you put units here, what you have is that this is about 100 seconds if your frequency is about 15 hertz, and the mass, the shear mass is about 1.2 solar masses. So this would be the case, for example, of a binary neutron star. A binary neutron star has masses typically of 1.4 solar masses. If you compute the shear mass, it's about 1.2 solar masses. So what this tells you is that if you start observing a binary neutron star at 15 hertz, it will be in your detector for hundreds of seconds. If you observe something which is more massive, like a black hole of 30 solar masses, that brings down this to a fraction of a second. And that's what we were seeing in the slides before. Yes, so then. In the? So this is, we have not put cosmology yet, so actually it's the same frame. But we are gonna do the cosmology in a second. Yes, so so from these expressions, what we saw is that the gravitational wave strain, h of t, it's gonna have an amplitude that is gonna increase, and then a frequency that is gonna become faster. And this is time, frequency. So from observing how the waveform changes, so how fast is the frequency evolving, which is essentially how rapid this is, the different peaks are getting closer to each other, you can get an inference of the mass. Now, this derivation here is the leading order term, which only depends on the shear mass. It's not by any means the only term. There are higher order corrections, and those depend in particular of the mass ratio. And the mass ratio gives you information about the asymmetry between the masses. So with the mass ratio and the shear mass, you can obtain information of M1, the two masses independently. But this is something that you do by fitting the data to your different waveforms. We will see a bit of this in the last lecture. Thank you. More questions? Okay, so what we want to do now is we want to put these gravitational waves into a cosmological background. So we want to study the cosmological propagation And this relates back to the first lecture in which we had derived that the general propagation equation was given by the D'Alembertian of the background metric on our metric perturbations plus 2 times the Riemann tensor of the background metric coupled to the metric perturbation. Now, before solving this, it's important to understand in which regimes we are. So, in particular, for a compact binary, as we are focusing on, the frequency of the merger is about, and you can derive this from these expressions that we have there, it's about 100 hertz if you have signals with masses around tens of solar masses. So if you think of this, this will give you wavelengths which are of the order of thousands of kilometers. Now, how does this compare to the relevant scales in cosmology? Well, they are actually very different. So like the expansion rate. So the expansion rate of the universe, that's about 70 kilometers per second per megaparsec. And if you remember that a parsec is 3 times 10 to the 16 meters. So if you, 1 parsec is 3 10 to the 16 meters, what you realize is that the frequency associated to the expansion rate is 10 to the minus 18 hertz, which if you put into a distance scale, and this is the horizon scale, c over h naught, this is about well, it's about the gigaparsec scale, which of course is much, much, much larger than the wavelength of our gravitational waves. So what this means is that actually for cosmological purposes, we can restrict to the case of geometric optics propagation that we did in the first lecture, where we study the properties, the propagation in the short wave expansion. So what this means is that actually to solve this, we need to solve in the short wave expansion, where we were seeing that the gravitational waves follow null geodesics and that actually the Riemann tensor is subleading. So the main equation that we need to solve is just box H mu nu. Is this clear? Okay, so that's what we are gonna do. But just before that, let's well, actually, no, let's do that now directly. So we are gonna solve this equation. And to solve it, we are gonna use some property of the D'Alembertian operator. So something to note as well here is that because we have neglected, as the scales are so different, the effect of the Riemann tensor, what you see is that the equations apply in the same way to all the polarizations. So actually, there is no mixing of polarizations. So we can study directly we can solve the equation for the polarizations H plus and H cross. So I'm independently. So I'm going to just call HA, referring to irrespectively one or the other. And then what we are going to use is this expression that tells you that the D'Alembertian operator you can rewrite in terms of partial derivatives if you include these terms which are square roots of the absolute value of the determinant. So let me just, and this is the background metric everywhere, G nu, HA. So this is just an equality. You can, if you want, it's actually not so difficult to solve. You can simply, you start from the covariant derivatives, introduce Christoffel symbols, do a bit of algebra, and you get there. But I'm not gonna do that derivation and just put this relation here, but just also we are having here, this is the absolute value of the determinant of the background metric. Okay? So we have an equation in terms of our perturbations and then the background metric. So we need to specify the background metric. So the case that we are going to focus on, let me write it here, is cosmological backgrounds that are homogeneous and isotropic. And for that, as it was explained in the first lecture of the school, you can describe this with a Friedman-Robertson-Walker metric. So we will consider a flat Friedman-Robertson-Walker metric, which I just write it again for your memory, is minus C dt a squared of t, and then I'm writing this already in spherical coordinates. Okay? So to solve the equation, it's going to be convenient actually to rewrite, to use conformal coordinates in which we write this metric taking out the scale factor so that we have something which is just the scale factor square times the flat spacetime. So this is Minkowski metric, but we have done it by defining we have defined the conformal time, which is dt divided by a of t. Yes? Okay, so here what we need is to compute the determinants. So we can do that. So the determinant, it's G is minus a to the 8, c squared r to the 4 sine squared of theta. This sine squared of theta is coming from the 2D sphere, this d of omega, and here, therefore, the absolute value, the square root of the absolute value of the determinant is just a to the 4 c r squared sine of theta. And then the other element that we need that will be useful is also that when you are in a cosmological background, the physical scales, they are stretched. So physical distances are stretched. So the physical distances as a function of time. This is the scale factor times the radial distances. And then we need one more element before we go into the derivation, which is that co-moving distances, then they encode they also encode the expansions, so we can get that, the co-moving distance, just taking null geodesics at a fixed angles. So this means that to take null geodesic at fixed angle, we have CD dt. This is a dr, and then these our co-moving distances. When we are in flat spacetime, this is just the coordinate distance r, and you can relate this to the time, the integral of c over dt over the scale factor from the emission to the observer. And then this we can rewrite in terms of redshift in the following way, which was an expression similar that we saw already in the slides. But this comes from the, you need to change variables, so you are changing dt over a of t. You say that this is dA over a, dt over dA, and then this is 1 over a over h, and then this is d logarithm of a over h, and then you can change this back to minus dz over h. Is this clear? I see that the rate of questions is decreasing. I hope you are still alive. The other days you were very much alive, and that was great. So maybe this is very familiar. Yeah, but these are notions of distances which are important. And then from here, one can define the luminosity distance. Which is dl 1 plus z, the co-moving distance, and this is 1 plus z, c dz over h of c. Okay, so what we are going to go back now that we have some of the formulae, is to solve the equation. And to solve the equation, what we are going to use is a spherical wave ansatz. So we solve using a spherical wave. And then what we are going to do, we are already anticipating a bit the result, but we are writing this spherical wave in terms of the physical distance. So we are writing a function fa, which is arbitrary for the moment, but then we are taking the spherical part, the scaling with 1 over the distance, to be the physical distance. So we have the expressions for the background metric. We have our ansatz for the perturbation. we need to plug this in and solve what f of a is. Is this clear, the strategy? Okay, so let's do that. And I think I'm going to do it here, actually. So what we need to solve is this equation. Notice that the 1 over the square root of the determinant we can throw away because the equation is equal to 0. So you don't need to worry about that. So then this is what we have. And then the first thing that we need to do is simply expand the derivatives. So we are going to have 1 over c squared, derivative with respect to the conformal time, a squared, r squared, derivative with respect to the conformal time, h of a, times derivative with respect to r of a squared, r squared, derivative with respect to r of h of a. So here I have only expanded the derivatives and take into account that the metric and its inverse are diagonal, and also the fact that the scale factor only depends on the conformal time. So if we include now the definition of our spherical wave, and we define here, we are going to define f prime a as the derivative of f with respect to c times the conformal time. So if we do that, then you get this fa double prime minus 2a prime divided by a f prime. This is, by the way, something which, if you haven't done this derivation for other purposes, I think it's always good to see how a wave propagating Friedmann-Robertson-Walker. And then you can rewrite this as fa double prime divided by a fa times second derivative of f over a. Okay, so I'm not doing all the little steps, but hopefully the logic here is clear. So what we have is something like this, and now it's this is, by the way, R. And then what we can do is that we can think of a wave solution for this equation. So if we think of a wave solution, that would be something like f of a eta to the r equals to e to the minus I omega eta minus r divided by c. Then what one realizes is that from these second time derivatives, what you're going to get, you're going to bring down 2 times the angular frequency, and then but this angular frequency is going to be much larger than this term. So this term here that we have is going to be much more subdominant than the frequency squared, and that comes from the differences in the rates between the cosmological background that changes in time scale of gigayears, while the gravitational wave changes in time scales of seconds. So if we neglect this term because of that, then actually this is a simple wave equation that we know the solution of. So from that equation, so I'm making this here to neglect that. Then we have h of a of eta r is just going to be our scaling that we have chosen. And then f of a, what is simply a function of the retarded time. So you see now why we were initially making this ansat is because then, well, that's, we were anticipating a bit the solution. But what you see here is something very important, which is that the gravitational waves, they scale with the inverse of the physical distance, which is also something I think than what could have intuitively expected. We can further take the normalization of the conformal time so that is equal to time at the present epoch. And then this expression, we can just simply write it in terms of t, r 1 over r a naught, t naught, sorry, and then you have f of a t minus r over c. Okay, is this clear? Are you alive? Yes, I see some hands. Great. Yes, please, please. Thank you for the question. What happened with the angular part? Yeah. Well, what we have seen is that the emission of the gravitational wave is given by the quadrupole. So actually, the angular structure is going to be determined by that. What we are here taking into account is the just the main the amplitude, if you want. But then when you take into account the right, the full tensor with the all the two polarizations, that gives you you can get the angular structure. Yes, on top. That's yeah, I think the question was related to whether these approximations are valid in the early universe, right? Yes, and the question is, the answer is no. So yes, so this is if you have, well, I mean, sorry, it depends on what you define as early universe, but as soon as you have changes in your scale factor at a rate which is similar to the frequency of the gravitational wave, then you cannot do what I'm doing here. But in the late universe, this is a very, very good approximation. Yes, so we are not accounting for lensing in any way. This is, we are doing the propagation in a homogeneous and isotropic background. Yes, so that's what we will do tomorrow. We will include, consider the case in which this metric is not homogeneous and isotropic. It has some density localized in a point, and then we will study that. Yes, yes. Yes. expansion. Yes. Yeah, but this is, as I'm arguing, is something that is an extremely good approximation for the purpose of gravitational waves from compact binaries and cosmological backgrounds. Yes, sorry. What I meant there is that the wavelength. Well, I erased that, but for these waves can be thousands of kilometers. So that's I mean that's big, but it's not as big as the horizon of the universe. Exactly, because that's what that's the scale that's relevant for the background. Good. More questions. Okay, so okay, great. So we have derived the change in the amplitude. Now we need to see what happens also to the frequency, and that's something that is related to a previous question of the frame in which we are doing the calculation. Yeah, so because the universe is expanding, the waves are going to be stretched, so they are going to suffer redshift. And then, so the frequency that we observe at the time in the detector, it's gonna be the frequency that was of the source at the time of the source divided by 1 plus c. So if we take the expression that we had before, we had this, so we have the 1 plus c, but then we had an expression for the frequency, which was 5 over 256, 1 over TC, well, let me say TS to the 3/8, GMC C cube minus 5/8. So what we want to do is that we have an expression of the frequency that we observe, but this is in terms of the time at the source. So this is something that we don't measure. So we want to change this to the time at the detector. So the time at the detector. Sometimes this I don't know what I'm doing. The time at the detector is 1 plus c, the time of the source. So if you put that here, then you have 1 plus 1 over pi, 5, 256, 1 over the time of the detector. And then what you have here is you have this 1 plus c, that is the factor here, and then you have the other factor here. So then what we are going to do is that we are going to reabsorb these factors of redshift in what is going to be called the detector frame mass, which is what it was shown in the colloquium. But what you realize is that actually, if we make this definition of detector frame masses, which is 1 plus c times m, actually the expression that we have of the frequencies observed in terms of the time of the detector are essentially the same ones from the frequency of the source in terms of the times of the source. So when you are in the frame of the detector, you are seeing essentially the same thing that we were predicting before, but the masses have to be redshifted. So there is, and this also is very physical because we were saying that the mass we infer from the rate of change of the frequency. So if you are stretching the wave, then you are changing how rapidly it changes. So then, therefore, your inference of the mass is going to be different. So there is this intrinsic degeneracy here. And this is for the frequency, but we can also write this for the full expression of the gravitational waves. And that will give us the expression that we need in order to do cosmology. So we have to do the same. So we have an expression from before of the H plus at the time of the source, but we want H plus at the time of the observer. So we have to put the scaling that we have derived here, the scaling with 1 over R, scale factor R, and then we have G, the shear mass square, 5/3, and then we have pi, the frequency at the source, C, 2/3, and then we have 1 plus cos square theta divided by 2, and then cosine of phi. So if we do the same as we have done here, we change to to the time and frequencies of the observer. Then what you find actually is that you obtain an extra factor of 1 over C that together with this scale factor times R gives you the luminosity distance, and then the rest is actually the same if you change the shear mass for the detector frame shear mass and you change the source frequency to the detector's frequency. So again, we are seeing that actually when the gravitational waves propagate in a cosmological background, the expressions that we derived yesterday are valid so long that you change frequencies from the source to the observer, and then you change masses to detector frame masses. So we have, and then also distances. Instead of having 1 over R, we have 1 over the luminosity distance. Instead of having shear mass, we have 1 plus C times the shear mass, and then we have frequency of the source to frequency of the observer, time of the source to time of the observer. Yes? So it's just a definition, but what you realize is that always the mass are going to come with a factor of 1 plus C. So actually, if you think observationally, you are not going to be able to distinguish these two. It always appears this combination, and we are seeing the same here. When you go to the definitions of, the observed frequencies, then that's what you can do. And actually, this has a reason, which is the fact that general relativity is actually, there is no scale in general relativity, so you cannot, if you redshift, you cannot distinguish the mass. But it's just a definition because it appears there. Exactly. So you get a 1 plus C on top here. Yeah, and then with the exactly. Yeah. Yes. So, and then I guess the thing, so for example, which is, the interesting thing for cosmology is that from the amplitude, you get luminosity distances, which give us information about cosmology. In the case of very nearby sources, like the binary neutron star that we observe, then you can approximate this at leading order in redshift. So you expand this at low redshift, and then what you get is just the Hubble law. So you can relate the luminosity distance to the H naught at low redshifts. But in general, one has to, in general, you have H of C, which is H naught, and then you have your cosmological parameters here. Yes, is this clear? Yes. Yes, so the question is how I replace this here. Yeah, so that comes actually from the solving this equation. When you solve the propagation in the cosmological background, what you realize is that the scaling goes with the physical distance, which is A times R, and not only with the distance. So the luminosity distance comes from the fact that you actually, when you are replacing when you are going to the detector frame frequencies, you have to do this game of adding these factors of 1 plus C. So some of them you absorb in the detector frame masses, but there is 1 plus C remaining that it goes in the amplitude. And that's what you absorb here. Yes. 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 The sorry. So this change to the mass? No. So this is coming from changing in this expression. You change from source frame time, which you cannot observe, to detector frame time that you can observe, and this gives you a factor of 1 plus C. And then you realize that with this factor of 1 plus C, it cancels out so that you, sorry, and I think this is 3. This must be a, sorry, I think I made a mistake, no? What is this? This is a third, I think. I think this is a third. Yeah. Yeah, so it just comes from absorbing the extra term. I encourage you to do it, actually, and you will see it. I did ground. So it's this one which is ground, no? Sorry, I did it wrong. I saw a typo in my in the notes, and I think, yeah. Thank you. Okay. So unless there are more questions, I'm gonna move on. I think I see people discussing, but okay. So, so we are almost at the getting actually the observed gravitational wave, but we need to do a bit of slightly a bit more work. So what we have seen actually is that we have seen that at leading order, our wave depends on the redshifted shear mass, the luminosity distance, the inclination angle, and some phase. So this comes from this expression: luminosity distance, detector frame mass, inclination angle, and then there is a phase which is inside there. Now, these are not the only parameters that define gravitational waves. Actually, and this has come in the questions, when you go to next orders, what you have also is you have the mass ratio, and importantly also you have the spin. So your black holes or your neutron stars can be, each of them can be orbiting with a given spin. So this is something that you can also derive analytically. I'm not going to do. What I want to now go is into the other remaining parameters, which come from the fact that we need to make a projection. And maybe I should actually, I'm going to do it here bigger. We need to make a projection between the frame of the gravitational wave into the frame of the detector. And what this means is that, for example, if we have gravitational waves coming from different parts of the sky, they are going to have different amplitudes in our detector. So we need to account for that. So we need to do a projection into the frame of the detector. And to see this, we need to see how the different frames are defined and how we go from defining angles from one to the other. This is something which there is in the lecture notes. You will see that there is some a diagram that is going to be probably much better than what I'm able to do in the Blackboard. So if something is not clear, well, you should ask now. But if you want a more neat version, I encourage you to look at the notes. Was there any question? I don't know, I think. Okay, so we are going to start in the frame of the source. So this frame of the source is defined by our binary, which is orbiting in a plane that we have defined to be the XY plane. So our binary is orbiting in this plane, and then it's gonna be the observer. So it's orbiting in this plane, and then the observer is seeing it's seeing the gravitational wave at a given inclination angle, Jn, theta Jn, and then there is also the fact that we need to define the orientation of the binary initially in this plane. So here we have several parameters. We have the inclination angle between the line of sight n and the total angular momentum, so theta Jn. We have the reference phase that has to be defined at a reference time, because you need to say at this given moment the binary is located is placed in this way. And then in this frame also, we have the masses, M1 and M2, and then we have the spins that I was saying. So these are the parameters that define in the frame of the source. But now, actually, we need to go. We want to go to the frame of the detector. So this is the, yes? So I'm doing all, yes, you need you mean the sky localization? Yes, that's what yeah. So to get the, I'm just, so, yes, I think, yes, hopefully when I put all the angles, it becomes more clear, but I'm defining only now the inclination of the, with respect to the orbital angular momentum. So in the detector frame, we will have our detector placed here. Our L-shaped detector is going to be in the XY y plane. And then we have theta d. So in this plane, our signal is going to come from some line of sight, small n, which is just minus big N. And then this position in the sky is defined by two angles that define the sky localization. So we have the sky localization, theta and bar 5, that tell you from which part of the sky the wave is coming. And we are only missing one additional parameter, which comes from the fact that our wave actually can be rotated in the plane where the polarizations are contained. So if we are in this plane that goes in the direction of n, and here this is the inclination angle that we had here. Then we need to define that, maybe this is the angle that you were referring to. You need to define a polarization angle that tells you how the polarization, the base of your polarization is aligned. So this is what I'm calling here the wave frame. And this is the polarization angle psi. So if you take all of this into account, we can count how many parameters we have. We have 1, 2, 3, 4, 5, and then 6 here, 11, 12, 13, and 14. And I'm missing one parameter, which I guess, yeah, you can, well, I don't know where to put it, but is the luminosity distance is the 15 parameter. So we see that our gravitational signal is going to be defined by 15 parameters. And what we need to do, the only thing that we are left with, we have seen how all of these parameters here in the source frame affect the signal. 1 second. But we need to see, maybe I should put this here just to make this. So this, we have seen how all of these parameters affect the signal. We need to see now how the polarization angle and the sky localization affect the signal. Yes? So these are 15 dimensions are the parameters of the compact binary of the source itself. This is not including anything about cosmology or anything about the population of the sources. Yes. More questions? Yes. Yes, so this is the fact that you have a freedom to choose the basis, how you define your plus and cross polarization, essentially. So, so this is n. Yeah, so you can rotate. Yeah, so yeah, depending on the Yeah, there is an extra freedom there to change the basis. Yes, please, if maybe you. Yes. Yes. This bar phi is from the sky localization, so that's telling you where the signal is coming from. Yeah, but yeah, so yeah, yes, yeah. So yeah, it's true. So yeah, so maybe an easier argument is that you need two angles to define J and two angles to define the sky location. Yeah, thanks. Yeah, that's much more clear. More questions? Okay, so what we need to do now is to see how these remaining three angles affect this signal here. And so to do that, what we need to do is we need to make the projection. So we have seen that our gravitational wave it's a sum of the two polarization plus H plus and cross. And here epsilon is the polarization tensor that we had also in the first lecture. H cross T. So what we need to do is we want to see what is the signal actually that you get in your detector that is going to be a projection of this wave into the frame of the detector, and this comes from this is something which is a property actually of the detector itself. So depending on the how your what is the shape of your detector, then you are going to have different antenna pattern functions. So here, so this essentially you need to take your matrices that define your polarizations, and you need to project them into some other matrices D, which are defined by your detector. But typically, this is absorbed into what is called this FA, which are where A is plus and cross, the antenna pattern functions. So these antenna pattern functions is something that you can compute for the shape that you have of your detector. So if you have something like an interferometer with an L, then what you have is that F plus is going to be a function of the sky position with this dependence, cos square, cos of 2 bar phi, and then F cross is theta bar phi cos theta sine of 2. So if you have, for example, and these are, by the way, the antenna pattern functions for the plus and the cross polarization. If you are interested in other polarization modes, the antenna pattern function will be different. Similarly, if you have a different configuration for your detector, this will change. But this is only including the direction in the sky. We need to include for the possibility of rotating the polarizations. So we need to have that. And then what we get if we include the polarization, rotation is the following. So we get F plus theta bar phi 0. So this is the expression that I have here. And then cos 2 phi f cross sine. So essentially the polarization angle, because this is a quadrupolar wave, changes with a factor of 2 phi. It's a rotation with a factor of 2 phi. Okay. So the important thing here, the actual dependence in the angles is not super relevant, I would say. But the important thing, which is that the signal itself that you detect, what you're gonna get in your detector is gonna be this f plus dependent of theta phi psi times h plus of t, and then you have f cross theta bar phi psi, and then you have h cross of t. So what this means is that depending, or for example, the location of the source, the amplitude of your detector is going, the amplitude of the wave is going to change. So, for example, if you have something which is coming from above, if theta is 0, then the contribution here is going to be maximal. And then also importantly, the polarization angle also affects the signal. Yes. Yes, so what I've done here to go from here to here is I've done a rotation of psi. So here in this plane, I have rotated psi. This, by the way, there are different conventions for this angle, so maybe if you look at a textbook, it can be slightly different, but yeah. Anyhow, it's just a rotation there. Yes? Sorry, which one? I couldn't hear. Yes, yeah, so I have not defined this. So this is, if you want, yeah, it's a property of the detector. So it's the detector response function. And then what I have not given you the detector response function, but I've given you the product of this with the relevant polarizations, the plus and the cross. So the so the plus polarization is this is epsilon plus, and the cross it's just the other one. So actually from you could reverse engineer if you want, but anyhow, yeah, what is more relevant to just directly think instead of the detector response function into these antenna functions, which are defined this way. Yes. Okay, so two things. First of all, the Earth rotates. So actually, we need, so it's important. I was talking about the detector frame, but actually what this we have done so far assumes that you are in the center of the Earth and you are not rotating. So when you to do so, it's typical to go to define the sky localization in terms of the right extension and the declination, which are just measures of the sky positions, but at a reference time. So the right extension is given by the angle phi times the Greenwich mean sidereal time, sorry. And then the declination is just a change here. So to define, to see how the, to get the sky localization and to, it matters, we need to take into account the time at which the signals arrive. And in fact, to get the sky localization, and this is something that I mentioned in the colloquium, but just we can give a bit more of the detail. So we have the Earth, and then we may have two detectors, one here and one here, and then we have a wave. Maybe we have a wave that is gonna arrive first to this detector, and then it's gonna arrive to the second detector. So we know that the arrival time at each detector is given by the some reference time minus the direction of the wave times, vector product of the localization of the detector. So this RD is the detector position on Earth, which is fixed, of course. So we know where our detectors are. So then if you compute the difference in arrival time between two detectors, the common arrival time goes away. And then you just get something which is the vector, the direction of propagation times the difference in the positions of the two detectors. But this is a vector product. So essentially, the quantity that you measure here is essentially some angle between detector 1 and detector 2. So what you get effectively is that with two detectors, you can say that your gravitational wave is located within one ring in the sky. And then if you have another detector, let's say here, then you could have another ring in the sky. And then the localization region that you infer will be the intersection of these two rings in the sky. So that's why having 3 detectors is actually much, much better than having 2, because you can constrain this. You can have the intersection, so by triangulation, you get a much better localization. Now, I mean, there is a bit of information of the sky localization just in the amplitude. So you can also do a bit better than this, but mostly if you look at the sky localization regions from real events, they are essentially just follow these degeneracies which are coming from the ring in the sky. Yes. That travels free? Yes, at the speed of light. So yes, so a given detector has a different, a predefined sensitivity to the different polarizations, but so the source properties change how much you generate of one polarization or the other. So something actually that kind of like related to that is that we have been focusing on the leading quadrupole radiation, but they are actually higher, they are other modes, higher frequency modes that the signal also contains. And for example, those, they depend differently on the inclination. So for example, if you have a signal that has asymmetric masses, then that signal is going to generate multiple frequency modes, and each of these modes depend differently on the inclination. So you could actually improve some of these things if you have signals which are a bit more complex. By gravitational? So So gravitational lensing, as we will see tomorrow, actually in the regime of weak gravity, which is what is most relevant for lenses in the universe, actually does not change the polarization. The propagation is the same for both polarizations. Yes. More questions? Yes? Yes. I love that you are all anticipating to tomorrow's class. So, yes, you should be excited about that. Yes. So so if you have the same signal, if you so I was saying in the colloquium that you when you have lensing, your initial wave can split can produce multiple copies. One of them can arrive first, another can arrive later. But these waves, they are coming from the same region of the sky, but they will arrive at Earth at different times. So the Earth would have rotated from one to the other. So actually, the detectors, if you are in the frame of the detector, you are seeing well, in other ways, let's say the other way around. Effectively, because you arrive at different times, you have the detectors at different positions with respect to the wave. So effectively, is as if you were duplicating the number of detectors because they are located at different points on Earth for the wave. So what this means actually is if you have multiple copies of the same signal and you know that those are coming from the same source, which is something which is difficult, by the way, then effectively you will be having more detectors and you would be constraining better the polarization. Yes. Yes. Yes, so yeah, so the thing is like the Einstein telescope, which is this proposed detector, future detector in Europe. Actually, the initial proposal is to have a triangle shape. So instead of having an interferometer, which is an L, you have a triangle, and this has different properties. Actually, in fact, this can effectively behave as two Ls, but But yeah, it's the antenna pattern depends on the shape of the detector. Yeah. So so the so depending on the antenna pattern function, your sensitivity at different points in the sky changes. So actually what you want to have, if you want to detect a lot of gravitational waves, is you want to have detectors at different points on Earth so that you are maximally sensitive around the whole sky. So gravitational wave detectors, they are whole sky surveys, but they have a bit of different sensitivity in different points. So if you strategically put detectors in different parts of the sky, for example, LIGO India will be very useful because it's very far from the other detectors and it would be in the southern hemisphere. That will help. If you were to put a detector in Australia, that will be amazing as well because you will have a better coverage of the sky, and that helps. Yes. Any final question? I think we are gonna finish it here. So I don't know if you have more questions. Yes. 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 Exactly. So it's no. You have only two independent because there are only two. Yeah. So there are with three detectors, you only have two independent arrival times because I mean, you have three arrival times, but only two of them are independent. The combinations. And that's why you have yeah. Any other question? Okay. Thank you for being with me so long today, and see you tomorrow.